There's a term that we call as instruction set completeness. What is that? When a computer is said to have complete set of instructions when it has sufficient number of instructions in all these categories. So if a computer has sufficient number of instructions, sufficient number of arithmetic instructions, logic instructions, shift instructions, instructions that are used to move the information between processor and memory, instruction that are used to control the program. So for example, I have to check status conditions, right? So this type of instructions are there in sufficient number. And for input and output, taking input from IO devices, sending output to IO devices, for this thing also, if there are sufficient number of instructions, then we say that it is a case of instruction set completeness. And what could be the various instructions? They are listed here, all three categories. So if I say this is the first category here, so this is the arithmetic, this is the first category, fine. These are the memory reference instructions, these are the register reference instructions, and these are the IO instructions. And we need to see them one by one. First of all, let us see here what is this hexadecimal code. And if I say that the instruction is 16-bit long, for example, so and I put them 16 bits in hexadecimal, they will be obviously 4-bit in a 4-letter code. And what will be the code for AND? We can easily calculate it like this. In memory reference instruction, there may be two cases. One where I is 0, another I is 1. I is 0 means direct address, I equal to 1 means indirect address. So for example, if I is 0, fine, and the opcode for AND we know is 000, fine. So the first 4-bit become 0000, fine, followed by an address of 12 bits. So 0000 in hexadecimal means 0, and the remaining 12 bits we can represent by a in hexadecimal like cross cross cross, implying that it is dependent on what the address is provided at that time, but it will be 3 digits in hexadecimal. In the same way, if it is an indirect address, in indirect address the I bit will be 1, and for AND the opcode is 000, so 1000 means 8, so this is 8, and then there is the address. If it is add, for add the opcode is 001, and what does it become here? It will become 0001, that is 1, and the remaining part is the address. What about here? The I bit is 1, then is the opcode is 001 001, 1001 is 9, then there is the address. And then similarly you can yourself know the hexadecimal code for each of these instructions. So for AND the opcode, we only need to know the opcode. For this the opcode is 1 in decimal. For AND it is 0 in decimal. For ADD it is 1. For LDA it is 2, 3, 4, 5 and 6. It is like this in decimal. So then correspondingly you can generate the hexadecimal code for direct address as well as for indirect address. And the second set, which is the register reference instructions, for that we know that the first 4 bits are always 0111. That's why everything here is starting with 7. And for input output instructions, we know that the first 4 bits are 1111. That is why all these are F, because in hexadecimal 4 ones means F. And whatever is here is the corresponding operation code. So this is the register reference instruction code here. For example, 800 is for CLA, clear AC, and other things. This represents the hexadecimal code for clearing the AC. So this code tells the processor that what operation it has to perform on a certain register. In the same way, this code tells which IO operation is to be performed. Fine. Let us now see these instructions one by one. Let us first of all see memory reference instructions. They are 7 in number. The first one is AND. The AND micro instruction is the meaning. What does it do? This instruction performs an AND to the AC. That is, this instruction takes a value, an operand from the memory, and performs an AND operation between the contents of AC and that operand. Fine. The AND will be obviously bitwise. So this is ANDing of contents of AC and the operand. So, but okay, we have value in AC first, but first we need to bring value from the memory. The operand we need to bring from memory. So that is why AND operation will constitute of these set of micro operations. So first of all, we need to bring operand from memory, and when we bring the operand from memory, it is a data. So data is brought into a data register. This means that from memory we go to a certain location AR, the address is given in address register, and then the contents are read to the register DR. Now we have brought the operand from memory into the processor register DR. Now we will do the ANDing thing. So now we will AND the contents of accumulator with the contents of data register. So this is a symbolic way of writing AND operation. So once this micro operation is done, the answer is again stored in the accumulator. And since this is over, the instruction has been executed now. So we put the sequence counter to 0. And when will these things happen? Uh, these things, according to the flow chart that we saw, the execution starts after T3. Since we are executing AND, so we can see it here. In this flow chart, we saw that up to T3, the first 3 steps are happening. Then the 4th step execution happens after T3. So the execution starts at T4. Right? Execution starts at T4. So that's why we are here writing in the execution of AND there are 2 steps, 2 consecutive steps. This happens in one clock cycle, and this step occurs in the next clock cycle, and these two occur simultaneously. So obviously this will happen in T4 and this will happen in T5. Okay. And another thing, what will be the decoder output when we do an AND? Since we know from here that in memory reference instruction here, what will be the decoder if this instruction is AND output? This will be, the first 4 bits will be 0 0 0 0. Fine, because AND is 0 0 0 0. 0 is the ith bit and the opcode is 000 for AND. Since the opcode is 000, that means the D0 line will be on. Since the opcode is 000 for AND, that means when we decode this 000, using a decoder, the D0 line will be on. Fine. So that is why we wrote here that D0 will be on, and the time cycle, the clock cycle will be T4. At this this instant, this micro operation will be done, and at the next, this will be done. The second operation, memory reference instruction, is add. Add means add an operand to the contents of AC. Again, this will start at T4 and it will happen at T1, because for add the opcode is 001. At 001, the D1 line of the decoder will be 1. That is why add will happen at D1. Next will happen LDA, because the LDA has a code of 010. That means D2 will be on, and it will be like this. Now D1, T4, at this time, what will happen? Add will happen, but before adding, we need the value that needs to be added. So first we read that value into DR, then the contents of accumulator are added to the contents of DR, answer stored in accumulator. Since we are doing an addition, maybe there may be a carry bit, so that carry bit, the carry out, will be stored in E, in a flip-flop. And since we are done, then the sequence counter will be put to 0. Third is LDA, which means load to AC. That is, move an operand from memory to AC. Fine. So from memory, we have to bring some some operand to AC. This can be done in this way. This again will not happen directly. It will happen in 2 clock cycles. First, the contents will be read, and we read something from memory that goes into DR. Then from DR, we need to transfer that to this thing, AC. Fine, and we are done. The fourth one is STA, store AC, which means that there is some value in AC, store it into the memory. So this is something like an write operation. Right? So it will happen in a single clock cycle, because STA opcode is 100. That means it will be D3, and the AC contents will be transferred to a certain memory location M. So in the memory at this location, AC contents will be stored. Fifth one is BUN, which means branch unconditionally. So it obviously um, will be D4 T4, and then this it will happen in a single clock cycle. And what is a branch thing? Branch means that we go to some other place. We are currently executing some instructions. For example, we executed the instruction number 5, then 6, then 7. Then from 7, we don't go to 8, we go to some other place. We jump to some other place. And how do we know that new place, the address of new place will be in address register? Right? So now PC should be updated, because PC, the program counter, contains the address of the next instruction. That is why PC currently will have the address of next instruction, but we don't have to go from instruction number 6, we don't have to go to 7, we have to go to some other place. That is why PC contents should be updated. So once we update the PC contents, automatically it will be a branch. And there can be another type of branch where we save the return address. That is, we branch to some place. Fine, we executed instruction number 4, 5, 6. Then we go to some other place, for example instruction number some other place 30. Then after executing that code, we come back to 7. That is why we need to save the return address. This type of branching is usually found in programming where we use procedures. So from one function, we just call a procedure. The procedure is executed, then we return back to the calling function, to the next instruction in the calling function. So this is what we call branch. But at the same time, we have to save the return address so that we can return back. So for this, first of all, we need to save the return address, then only we can branch. So first, we need to save the return address. What is the return address? That will be obviously in PC, because PC contains the address of next instruction. So the return address will be in PC. We first write it in memory for the purpose of saving. So we just saved this thing, fine. Then we went to the next position in AR, where we may find the new procedure address, fine. Maybe that it is here. So from this place, we put this address in PC now. So the PC is overwritten now with the new address, branch address. Now here branching is occurring. So this is saving. So we need two clock cycles. In one clock cycle, we save return address, and in the next, we branch. And the 7th memory reference instruction is ISZ, which means increment and skip if 0. This is executed in 3 clock cycles. So it says that we have to increment. What increment? We have to increment the contents of DR. So the data obviously will be in DR, data register. We need to increment it, just add 1, fine. But we need to do this skipping also then after adding 1. So first we need to increment a certain operand. The operand initially will be in memory. First of all, let us bring that from memory into DR. Once the operand is in DR, in the next clock cycle, the DR is incremented. And to increment DR, we don't need the help of other circuitry, because there is a direct, we know there is a direct control signal INR increment that goes to the DR. So that signal will increment the DR. Done. Now the next step is skip if 0. So what we have to check, okay, before that we need to save the DR back to memory, right? We took an operand from memory into DR, increased that operand value by 1. Now we need to put the new value back to the same memory location. And so this is reading, then incrementing, then this is writing. So this is the increment part actually is done. Now we will also check the value of DR. If the value of DR is 0, that is what it means, skip if 0. That if the answer is 0, then you skip the next instruction. What is to be skipped is the next instruction. So if I tell you just skip the next instruction, you are currently executing instruction number 6, just go to instruction number 8. Don't execute instruction number 7. What will you do? You will just increment the contents of PC, right? Because PC contains the address of next instruction, and we will skip it by adding 1. By this, we will do the skipping, and then this whole operation is done. Finally, the sequence counter will be put to 0. Now let us study register reference instructions. A register reference instruction is one that operates on the contents of a register. In this instruction, there is no memory reference. The particular operand or the operation is to be performed on the contents of a register, of a CPU register. And we know that when we see the format of this register reference instruction format, so if there are 16 bits, in those 16 the initial 4 bits will be 0 triple 1. 0 triple 1 will mean it is a register reference instruction. Then the remaining 12 bits, they represent what type of register reference instruction is this. And how do those 12 bits specify the instruction? Simple. If the if I say that the bits are 0 to 11, right? If the bits are 0 to 11, like here, you can, so this is a register reference instruction. This 12 bits is 0 to 11. If the 11th bit is on, that is, this is 1, that implies it is the first instruction, right? So the clear accumulator instruction. If the second bit here on this side, most significant bit, that is um, the next bit, the 10th bit is on, that means it is the next instruction. If the 9th bit is on, it means the next instruction, and so on. So it, at that time, all other bits will be 0, only that bit will be 1. And how many combinations can be in such a way? There can be 12. So the first instruction will be 1 followed by 11 zeros. The second will be 0 1 followed by 10 zeros, and like that. There will be in total 12 instructions. So these will be the 12 instructions. So for the first instruction, the first instruction is CLA, that is clear accumulator. And for this, the 11th bit, let us say, if I say that the instruction register is having that 0 to 11 bits, and let us call each bit by BI, fine. So here, if I say B11, that means the 11th bit is 1, then only this clear accumulator will occur, and all other bits will be 0 at that time. The same way, the next instruction is clear E, and the E flip flop, and for that it is 10th bit, so B10, like that, B9, B8, B7. So it all goes like this up to B0, right? So in total it will be 12 instructions. And for the same, we can also see the hexadecimal here. So if I want to put those 16 digits of the instruction format in hexadecimal, what will be it like? It will be, the first 4 bits are 0 triple 1, that is 7, and then followed by 1 and 11 zeros, that means this thing in hexadecimal, 800. The next is 011, that is 7, followed by 0 1 and then 10 zeros, so that will be 400. And in the same way we can uh, remember all these codes, right? The actual thing is binary code, but for making it easy to write, we can put it like this in hexadecimal, the various codes for the various instructions, register reference instructions. Okay, now another thing is that when does a register reference instruction get executed? Again, let us go to this flow chart that we have studied. So we know that D7 should be 1, I should be 0, and the clock cycle should be T3. So it will be D7 I dash T3, right, for register reference instruction. So that means here for register reference instruction it should be D7 I dash T3. Let us call this thing as R. This implies that these lines should be 1. D7 should be 1, I should be 0, and T3 should be 1. And let us call this R. So if I go to this instruction, if there is only R, that is this in total is 1, then obviously the sequence counter will be set to 0, right, as is there in the flowchart. And if R, that is this is on, implying that we are in a register reference instruction, and then B is 11, R is 1 and B11 is 1, fine. So if B11 is 1, that implies we have to clear the AC. So that time the contents of the accumulator will be cleared, that is they will be put to 0. And the next is clear E. So at this thing R and B10, the E flip-flop will be cleared. Next is CMA, which implies complement accumulator. So at this, the accumulator will be complemented. Each bit of accumulator will be complemented. Next is CME, complement E. So the contents of the E flip-flop will be complemented. And next is CIR, that is circulate right, meaning this is shift right the contents of accumulator, and but the shift should be circular shift, right? So this is circular shift right. So what is a circular shift right? We take the least significant bit of A, put it in E, move all the contents of accumulator to the right, push them to the right, and at the leftmost position, at the most significant bit, you introduce this E. So this is a circular way. The shift has been done in a circular way. So the least significant bit becomes the most significant bit, and the shift is also happening. In the same way, if I have to do CIL, that is circular left, that is I have to shift the contents of AC to the left in a circular way. So I will take the most significant bit of AC, put it in E, shift the bits of AC to left, and that E will be put at the least significant bit. So this is circular left. And this increment AC is this B5. So AC will be incremented by obviously by 1. Next is SPA, which means skip if positive. So if the contents of accumulator are positive, then we have to skip the next instruction. How to check whether the contents of accumulator are positive or not? We will check the most significant bit of AC. So if the number inside AC is a signed number, the most significant bit represents the sign. So if the most significant bit in AC is 0, that means it is a positive number. So if it is a positive number, we have to skip. Skip means that we will add 1 to the program counter. So next instruction will be skipped. Skip if negative. So again, if we check the most significant bit of AC and that bit is 1, that means the number is negative. So if the number is negative, we do the skipping. Skip if 0. If AC is 0, so just check the contents of AC. If it is all 0, then skip the next instruction. Skip if E is 0. Right? If the E is 0, the E flip-flop, we know it stores the carry bit. So if this is 0, then skip the next instruction. And last is HLT, which means halt the computer. The halt computer, whenever halting is to be done, this should be 1, and there is a S bit, S flip-flop in the processor, that is called a start stop flip-flop. This flip-flop will be put to 0, which will halt the processing of the programs. It will halt the computer. So these are the 12 register reference instructions. And the third category is input output instructions. These are those instructions that deal with the input and output to the IO devices. So processor wants to take some value from an IO device, for example keyboard, or it wants to output something, some character to an output device, for example printer. So how will be that done? If something is coming from the keyboard, it will go to the input interface. Then from that input interface, the character will move to the input register of the processor. Fine. So if something is coming from keyboard, first it will go to input interface of the keyboard. Then it will go to the inside the processor. There is a register called input register INP. It will go into that INPR. It will go into that, and at the same time there is a flip flop that is called FGI, and input flip flop. Input, there's a flip flop. When it is set, it acts as a flag. So FGI implies flag input. So if that flip flop is set, that will tell the processor that a character is coming. Fine. So first the character will be written into the input register, and at the same time a flip flop will be set. This will act as a flag and will tell the processor that a character is coming. Okay, now so that means if I have to do input, that what will happen? Input flag FGI will obviously be 1 at that time. That means the accumulator will take the contents from the input register and bring them into accumulator. So this is input. The contents have already come into the input register. Now they have to be transferred from input register to accumulator. So this is INP in instruction. Now since what is coming from the keyboard is just a character is of 8 bits, so only 0 to 7 bits of the accumulator will be used. So the transfer will be to this part, right? And if at the same time once the input is done, then we have to reset this flag, input flag. Now if output is to be done, for example it is to be sent to the printer, then the one character from AC will go to the output register. Fine. And then the flag output will be reset, output this flag. And then if I want to do skip on input flag, right? So I have to skip an instruction if the input flag is on. Just check the input flag. If this is 1, then skip the instruction. SKO, skip on output flag. If the output flag is 1, just skip the instruction. Next is interrupt enable on. Interrupt on, right? So it means that just put the interrupt line on, put it to 1. Interrupt off means put the interrupt line to 0, put it off. Right? And when will this input output instructions be executed? We know from the same flowchart that D7 should be 1, I should be 1, and T3 should be on. Then input output instruction is executed. So it will be D7 I T3. So for this to be executed, it will be D7 I T3. And what will be the format? And we know that for input output instruction, the format is the first 4 bits are 1 1 1 1. So the first 4 bits will always be 1, fine, which in hexadecimal means F. So the first 4 bits will always be this 4, 1111. Then these bits will represent which type of operation we are performing. Since IO instructions are only 6 in number, so only the most significant 6 bits will be used here. Out of these 12 bits, 0 to 11, there are 12 bits, only 6 bits will be used. Which one? These most significant. So it will be 11, 10, 9, 8, 7, and 6. Right? So these will be the 6 bits that will be used. How will it happen? If the most significant bit is 1 and other are 0, that means it will be the first instruction, that is the INP input. If the second bit here is 1 and others are 0, it will be the second instruction, and like that, right? Up to 6 positions it will happen. So that is where we can deduce this hexadecimal code. So for input output instructions, starting it will be 1111 followed by 1 and all zeros, that means 800, then 01 and all zeros, this will be this, and so on up to only 6 instructions, because there are only 6 in number. And so this should be like this, D7IT3. And if I represent the ith bit of IR as this 6 to 11 as BI, so this will be like this. So for input, this will be B11 should be 1, B10, 10th bit should be 1, 9th bit should be 1, 8th, 7th, and 6th. So these are the various input output instructions of a basic computer.